India's most comprehensive preparation platform for all the engineers. All the candidates who are live with me, just quickly confirm your presence in the comment section so that we can start with the session. Until you're going to report me this, let me just brief you what is the ideal duration and what is the agenda for today's session. Friends, the ideal duration for today's session is going to be approximately 2 to 3 hours. And what is the agenda for today's session? You must be aware that we have started with the Maha-Marathon series, technical portion also, non-technical portion also for engineering services examination. The GATE exam is over, so definitely the next target has to be engineering services examination. And you must be trying to know that, sir, what is the motivation for engineering services? So I will just show you this. This has to be your motivation why you should go for engineering services examination. So if you want this, if you want that much respect, recognition and contribution in the nation building, and you just don't want to do a job and you want to get into a service because it is engineering service, it's not a job, it's not just a job. Apart from the other attributes of a job, it is kind of profession. So let us start quickly with the session. The subject we are going to start today is material science. Now, material science is a subject which is the major difference between the GATE syllabus and the engineering services syllabus, you can say. And if you see the previous year pattern for material science, especially for engineering services, you must be aware that this subject has got significant weightage in the previous year. The questions are quite simple, but you must be little deep into the concept. So all the candidates who are live with me, just quickly confirm your presence and tell me, are you able to follow me? Just everybody tell me in the comment section, are you able to follow me? Shall we start? So before I start, some of you may be joining me for the first time. So there is a brief introduction about myself. My name is Ashutosh and I have more than 11 plus years of teaching experience, completed my MTech in 2010. I have written a couple of books and I deal with various technical and non-technical subjects. So I'm dealing with material science also. Before we start the session, 15th of February, for the first time, BYJU'S Exam Prep. Abhishek Kumar is asking, sir, whatever you discuss in this session, is it for paper 1 or paper 2 for material science syllabus? Very interesting question. So let me answer it in a proper way. This is engineering services prelims examination and this is Maha-Marathon for electronics and electrical candidates only. So this is a core subject. This is a core subject. For ESE electrical, it is a core subject. It is a core subject. It is not for all. It is not for all the branches. For other branches, we'll be having that session is tomorrow. That session is tomorrow, and that session will be taken by me and Dheeraj Sardana sir, where he will be talking about the mechanical portion, and I will be talking about the electrical and electronics portion. Okay. So I hope Abhishek, you got the point. This is the core subject for electrical and electronics that we are discussing right now. One more important thing I want to say that we are going to have 2 sessions for material science. So today is going to be the first part. Today is the first part. The second part is going to follow soon. Yes, this is for paper 2. This is for paper 2. Perfectly. This is for paper 2 of the engineering services prelims examination. I hope now it's clear. So let us quickly start with the session. So I was saying that 15th of February 2023, for the first time, BYJU'S Exam Prep is launching the rank predictor for GATE 2023. So if you have attempted the GATE examination, you should not lose this opportunity. The moment you get the responses from the GATE official website, you fill those responses in the rank predictor and you will get your most probable rank. Akash Pandey is saying, sir, I have not prepared for non-tech. Following the marathon is enough. Yes. You don't say it's enough. What other choice do you have? What other choice do you have? Okay, that is the reason. But for this, you have to register yourself. So please register yourself for the rank predictor. Now Rakesh sir is bringing one interesting session for the BAR 2023 examination, because all those candidates, for any reason, if they might not have performed well in the GATE examination, now BAR is going to be the next opportunity for your job. So I think Rakesh sir is going to tell everything, that what is the difference, what is the similarity as far as the GATE examination is concerned, and definitely we'll be coming up with more and more sessions for these type of PSUs and career opportunities. Now, UPSC Engineering Services Prelims Examination 2023 live exam analysis we are going to conduct on the same day of the examination, that is 20th It is 19th of February. Okay, sorry, 19th of February for paper 1 and paper 2. Paper 1 we'll be doing at 5 p.m. in the evening, and paper 2 will be doing 6 p.m. in the evening. So be ready to attend this live analysis of engineering services. It is important. And subscribe to the channel if you have not subscribed, so that you do not miss any of these important sessions. Okay. So shall we start? Everybody just tell me. Everybody just tell me, shall we start? Yes, everybody. So let us start with the very basic and very fundamental part, because this subject requires a lot of theoretical output. So you have to have a little bit of patience, because in the starting we'll be slow and we will try to cover the maximum part of your syllabus so that you feel confident. And I can assure you that whatever we are discussing, there is a high possibility that you will see questions from this discussion. So take it very seriously. Wherever you want, you can make notes also. And if you already have the notes, you can just highlight the important points what we are discussing. So if you ask about the very basic fundamental part of any material, so that is an atom. Atom is the smallest unit which is indestructible, beyond which you can talk about the subatomic particles. But atom is the most stable part which can exist in its totality, and any material's fundamental unit is going to be atom. So you can say an element is a substance that cannot be broken down into another substance. For example, we have the periodic table. In periodic table we have different elements, and those elements are unique in terms of their various physical and chemical properties. You can say physical properties includes mechanical properties also. So these elements are they cannot be broken down into the another substance, and atoms are the smallest unit of an element that participate in the chemical reactions. So you must be aware that any atom is going to have a nucleus, that is the central part, and this nucleus consists of neutrons and the protons, and the electrons are going to be orbiting in various elliptical orbits. Is it clear, everybody? Is it clear, everybody? Next, let us talk about the chemical bonds. Now you must understand that similar atoms or dissimilar atoms, if they have to join together, if they have to form a material, then definitely we need some force, some attractive or repulsive force, or a combination of it. So chemical bond is nothing but a binding force, and this binding force is the sum total of attractive force also and repulsive force also. I hope you can understand. So it is the binding force between the atoms in the molecules, and it is a kind of force which attracts or repel. So please understand, when you are getting the assertion and reasoning type questions, every single word is going to be important. When you read the question, you should read the question very carefully. So it can be attractive also, it can be repulsive also, so that the atom on the molecules are united and stable Okay. Now what is bond energy? Now please understand, whenever a bond is formed between two atoms, maybe similar or maybe dissimilar, it requires certain energy to break. It requires, just give me a moment. Okay. Okay, so in order to break that bond, you require some energy. So that energy you can call as bond energy, or in other ways you can say the amount of energy which is required to separate a particle from a system of particles, or to disperse all the particles of the system, that is called as bond energy. It is also known as binding energy also. So you should not confuse, these are not two different things. Bond energy, binding energy is the similar thing. The basic idea is the atoms constitute similar or dissimilar atoms to form a material. Now in order to separate these atoms in isolation, how much energy you require, that is bond energy. Binding energy is especially applicable to subatomic particles in the atomic nuclei, to electrons bound to nuclei in atoms, and to atoms and ions bound together in crystals. Let us talk about the bond length. Now bond length is one important criteria which depends upon the atomic radius also, or you can say atomic radius depend upon the bond length, because the bond length is going to decide various physical and chemical properties of any material. So how we are defining the bond length? It is the length of a bond is defined as the center to center distance of the bonding atoms. Center to center distance between the bonding atoms, the two atoms which are binding together. Now the strong bonds pull the bonding atoms closer together and so have a smaller bond lengths as compared to the weak bonds. This is but natural. If the bond is going to be very strong, then there may be a little overlapping, so the bond length is going to be less than the diameter. It is approximately same but little less. Whereas in case of weak bonds, this attraction force is not going to be that much, so bond length is going to be little more than the diameter of the atoms. Now primary bonds and secondary bonds. We will be defining the primary bonds and secondary bonds under the chemical bonds. Primary bonds are generally those bonds which have higher binding energy. They are very strong bonds. And secondary bonds are those bonds which have comparatively less binding energy and they are weak in comparison to the primary bonds. So primary bonds have bond lengths in the range of 1 to 2 angstrom, and the secondary bonds are larger in the range of 2.5 angstrom. So you can understand the secondary bonds are going to have larger bond length in comparison to primary bonds. Everybody just tell me in the comment section, are you able to follow this or not? Very important point I am discussing. Very important point I am discussing. The bond length is going to be more or high for primary bonds in comparison to secondary bonds, because primary bonds are stronger bonds. Next, now the length of the bond can be used to define the atomic or the ionic diameters. When bonding is between the two neighboring atoms of the same kind, the atomic diameter is simply equal to the bond length. The mean bond length increase on heating. In other words, the material exhibits thermal expansion. Now what happens when you increase the temperature? When you increase the temperature, it will lead to lattice vibration. This lattice vibration will lead to an increase in the bond length. Is it clear, everybody? Tell me yes or no. I am not getting your comments in the comment section. So if you increase the temperature, what will happen to bond length? Bond length is going to increase. Classification of bonds. Atomic bonds in general can be divided into two parts, that is the primary bonds and the secondary bonds. As I told you, primary bonds are those bonds which are having comparatively higher binding energy. Comparatively higher binding energy. Whereas if you talk about the secondary bonds are those bonds which have comparatively less binding energy. Less binding energy. Now there can be sub-classification for primary bonds. For example, ionic bonds, covalent bonds and metallic bonds. Covalent bonds can be further divided into sigma bonds, pi bonds and hybrid bonds. If you talk about the secondary bonds can be sub-classified as dispersion bond, hydrogen bond and dipole bonds. Is it clear? So let us first talk about the primary bonds. As I already explained to you that primary bonds are going to be very strong bond. They are stable and strong. They are interatomic bonds. They have comparatively higher binding energy. For example, ionic, metallic and covalent bonds. Now the attractive force between a positive ion and a negative ion causes an ionic bond to form. Now I want to ask you a very simple question. Everybody ready for this question? Ionic bond is going to be a positive ion, that is cation, and a negative ion, that is anion. Now these two ions having the different charge, they are going to have the attractive force between them. So don't you think they are going to collapse together? Yes or no? Because positive and negative ions, they are going to attract each other, so they will collapse or not? Definitely they will not collapse. Why? Because when you are at very close to the atomic distances, there is a very high repulsive force which comes into the existence. Now this high repulsive force is going to balance out the electrostatic force between the positive and negative ions, cations and anions, and that is how you get a stable system. The bond which results due to the electrostatic interaction of the oppositely charged ions, that is by the transfer of electron from one to other. Now suppose two atoms are taking part in the ionic bond. So one atom is going to have excess of electrons in the outermost orbit, and one atom is going to have deficiency of electrons in the outermost orbit, because every stable atom has to achieve the octet rule, that the outermost orbit must have the 8 electrons. Yes or no? Now the key word you have to remember for the ionic bond is that it is due to the transfer of electron from one atom to the another atom. Generally the dominant ionic bonds are formed between the group 1 and group 7 elements of the periodic table. Can you remember your class 11th and 12th? Group 1 is related to alkali metals and group 7 is related to halides. Yes or no? Chlorine, bromine, iodine. So these two elements, they get the best of the purest, you can say, form of the ionic bonds. So the best example can be sodium chloride. Now if you see the atomic structure of the sodium, the outermost orbit is having one excess electron. You see this outermost orbit for the sodium atom, it is having one extra electron, and if you see the chlorine atom, it is having a deficiency of one electron. It has 7 electrons, 1, 2, 3, 4, 5, 6, 7, 7 electrons in the outermost orbit. So there will be a transfer of this excess electron from sodium to chlorine, and because this sodium atom, it has given out one extra electron, so it will get a positive charge because electron has the negative charge. When negative charge goes out, automatically it gets a positive charge, and this is called cation. This is called cation. Now the chlorine atom, it has got one extra electron. Electron is negative in charge, so definitely chlorine is going to have a negative charge. This is called anion. Everybody just tell me in the comment section, are you able to follow this? Is it clear? I hope you are getting the idea. Ionic bonds are unidirectional, very important. They are unidirectional because the transfer of electron can be from one side to other side. It cannot be vice versa. So it is obviously unidirectional. The ionic bonds form compounds which have the following characteristic. Ionic bonds are going to be strong bonds, so definitely the structure is going to be crystalline in nature. It has high strength and hardness, and it has higher melting point. Now electrically it is insulated, so you can take the best example of salt. How many of you have eaten the kulfi, cycle wala kulfi? You remember? If you belong to middle class, you must have seen this. People are having a pot, what we call is earthen pot, and there is a rock salt. Between this, they used to put the kulfi, that ice cream, and it is not melting. Why? Because salt acts as a very good insulator. But at the same time, you should not confuse with the Three Idiot movie. In the Three Idiot movie, it is said that the aqueous solution of salt, it is conducting. So in the aqueous solution form, in the solution form it is conducting, but in the solid form, in the crystalline form, it is the best of the insulator. It is the best of the insulator. And it is brittle. What is the meaning of brittle? If any metal is brittle and if you hammer it, it will be broken down into small pieces. That is called as brittleness. Now let us talk about the covalent bonds. Now if you are saying that ionic bonds are because of the transfer of electrons, then you can say covalent bonds are because of the sharing of electrons. Okay. Now when sharing will happen? When sharing will happen? When transfer is not possible? Hello? Very important point I am discussing. You will not find these conclusions in the book. Sharing screen is blur. Okay, I hope you are using a good quality mobile or something, Tushar. Refresh your page, Tushar. I think there is some problem with your internet connection maybe, or maybe your download speed. Everything is clear. I can watch it in my mobile. It is very good. You can see it. Parallelly, I am watching the comments. That is why. Can you see? It is quite visible. It's quite visible, yeah. Okay. So दिखावो पे मत जाओ, अपनी अगर लगाओ और अफवाहों में मत फंसो दोस्त, अफवाह मत फैलाओ, ठीक है? So what I was saying, covalent bonds is because of the sharing of electrons. What is the key word? Sharing of electrons between the atoms. Covalent bonds are directional in nature. Covalent bonds are directional in nature. Why covalent bonds are directional in nature? I will tell you later on in the same part of discussion. Please have some patience. The examples are hydrogen, carbon, fluorine. For example, you can see chlorine. Now, chlorine is having 7 electrons in the outermost orbit. So, this chlorine atom is also having 7 electrons in the outermost orbit. Now, do you think there can be transfer of electron? No, it's not possible, because if there is a transfer of electron from one atom to another atom, one atom will definitely complete the octet rule. But what about the first atom? It will have 6 electrons. So, when the transfer of electron is not possible, sharing of electron is completed. Now, sharing of electron means, now these 1 electron from this chlorine atom is going to be shared by this chlorine atom, and this electron from this chlorine atom is going to be shared by this chlorine atom, so that both of them are having the complete octet. That is the 8 electrons in the outermost orbit. Is it clear? Now, what is this short range repulsion? Okay, let us understand. The assumption that the ions are point charge. So, I think it is misplaced. It is basically for the ionic bonds. Okay, so don't get confused. Don't get confused. The assumption that the ions are, already I have explained it to you. Already I have explained it to you when I was saying that the positive and negative charges coming together. So, why it is not getting collapsed? So, the reason was the short range repulsion. The assumption that the ions are point charges will be valid only when the electron clouds surrounding the two nuclei do not overlap. And it is very logical also. If the electron cloud is going to overlap, there is a possibility that Pauli's exclusion principle is going to be broken. What is Pauli's exclusion principle? Pauli's exclusion principle says that no two electrons can have all the 4 quantum numbers same. Yes or no? You remember it. You have read it in the intermediate. But if there is the overlapping of orbits, then there is a possibility. So he is saying the Pauli's exclusion principle will come into the picture if there is an appreciable overlap. If there is an appreciable overlap, then Pauli's exclusion principle is going to come into the picture between the 2 electron clouds. Not more than 1 electron can occupy a given quantum state, and this give rise to a repulsive force. This would develop a very strong repulsive force between the ions, which is short range. Short range means it will only come into the picture when the distance is very small at the atomic or subatomic level. Okay, for large distances it is not present. Now, when the electron clouds start to overlap, the repulsive force increases very fast, sharply, with decreasing distance. Let us talk about the Madelung concept. Sorry, Madelung constant. This can be asked, okay? Very important one. So, Madelung constant, what it is, let us understand. As the ionic bonds are non-directional, a cation in a crystal, cation means positive ion, in a crystal tends to surround itself by as many ions as possible and vice versa. Very, very important part, and please understand this. Suppose this is one atom, this is one atom. Now this atom has 1 extra electron which it has transferred to this atom. So what will happen? 1 electron transferred means what? This is cation, and its size is going to be what? Size is going to be less because the outermost orbit has gone. There is no electron. Hello? Are you able to follow this or not? The outermost electron is gone, is being transferred. It means the size has been reduced. Now the second atom which has received the electron, second atom which has received the electron, it has got one more orbit. So this is anion, and its size is going to be increased. Yes or no? So if I have to show you the cation and anion, how I'm going to show you? It is going to be something. This is going to be your something like this. This is going to be your cation, positive charge. And something like this. This is going to be your anion. So what he is saying, the ionic bonds are non-directional and a cation in the crystal tends to surround itself by as many anions as possible and vice versa. So whether you talk with respect to the negative ion or you talk with respect to the positive ion, there will be a closed packed structure. Closed packed structure means how much possible space can be occupied, that will be occupied. So this positive ion or cation is going to be surrounded by as many negative ions or the anions as possible as per the geometry. Hello, are you able to follow this? Everybody. Next, the Coulomb's term for a crystal is then dependent on the mutual attractive as well as repulsive interaction of a given ion with all the other ions in the crystal. So it is going to be attractive also and it is going to be repulsive also. You may get an assertion reasoning question multiple times, I am saying, and if it comes, you should not do the mistake. The example is attractive interaction with the nearest neighbors. Listen, attractive interaction with the nearest neighbor. This is positive, this is negative. It is attraction, but there may be another positive, so there will be repulsion also. Repulsive interaction with the next nearest neighbor, which are of the same sign. भाई एक पॉजिटिव था, एक नेगेटिव था, इनके बीच में था अट्रैक्शन, बट एक पॉजिटिव यहां पर भी तो बैठा हो सकता है. There may be one positive ion here also, so there will be repulsion also. So it is the sum together of attraction and repulsion force. Now this is an interesting problem in the spatial array. Spatial array means how the atoms are going to be oriented or arranged in the three-dimensional space, that is called as a spatial array of the ions, and was first solved by Madelung. The Coulomb energy term for a pair of isolated ion is simply multiplied. Listen very carefully. The Coulomb energy term for a pair of isolated ion. Isolated ion means what? One positive, one negative. This is isolated ion. But in a material, there will not be only one positive and one negative ion. There will be so many cations and anions. So he is saying the Coulomb energy term for a pair of isolated ion is simply multiplied by a constant, and that constant is Madelung constant, to obtain the energy of a pair of ions in the crystal. Hello? Are you able to follow this? What is Madelung constant? This constant is called the Madelung constant, and it is 1.748 for sodium chloride type crystal and is 1.763 for a cesium chloride type crystal. You don't need to remember it, just for the sake of reference. If you want to know, remember, you can remember it. But the idea is, from the isolated one to the crystal one, you have to multiply to get the real or actual value of the Coulomb energy, because there will be a combination of attractive and repulsive force. Now let us come back to the covalent bond. These are the various characteristics of the covalent bond. These bonds are formed due to the sharing of electron. They does not form close packed structure. They are very hard, very high melting point. Listen very carefully. The ionic bonds material, they are also having high melting point, but they are having very high melting point. Are you able to follow this? Ionic bonds material, high melting point. They are having very high melting point. They are having hardness. They are very hard. They are brittle. It is very brittle. Example is, if you talk about the conductor, then tin. For insulator, diamond. For semiconductors, silicon and germanium are going to be the best examples of covalent bond. Let us talk about the type of covalent bonds. The type of covalent bonds you can define as three types. For example, sigma bond, pi bond and hybrid bond. You first understand the sigma and pi bond, and then hybrid bond is going to be a mixture of it, you can say. Let us talk about the sigma bond. Sigma bond we are defining as a result of head to head, or you can say axial overlapping of the atomic orbitals. Axial overlapping of the atomic orbitals. Sigma bonds are formed as S to S, S to P, P to P overlapping. For example, this is S orbital, this is S orbital, and you are getting S and S overlap in the axial manner, along the axis. Is it clear? For example, I think it is visible to you. If you see the comparison between the sigma bond and pi bond, first we'll come to this comparison later on. Let us first talk about the pi bond. Now pi bond is going to have side by side overlapping, or you can say lateral overlapping, not like this, like this. So pi bonds are formed by the sidewise positive overlap of the atomic orbitals along a direction perpendicular to the internuclear axis. You can see this is the p atomic orbital, and they are going to be connected like this. They are overlapping like this. Okay. So this is the pi bonding. For better understanding, you can see the difference by these two diagrams. Both of them are p orbitals. So when it is head-to-head overlap, when this is axial overlap, then this is sigma bond. And this is side-to-side overlapping, side-to-side lateral overlapping, then it is going to be pi bond. This is going to be pi bond. Is it clear, everybody? Just tell me yes or no. Now you can compare it. See the comparison table. Yes. Formation due to, so for sigma bond it is going to be the axial overlapping. For this is sigma bond, I think it is not visible. This is sigma bond and this is pi bond. Okay, so this will be axial overlapping for the sigma bond for the formation, and there will be lateral overlapping for the pi bond. The extent of overlapping, for axial overlapping, the overlapping will be higher, it will be greater, whereas for lateral or side by side overlapping, it will be smaller. What are the orbitals which are involved and their axis? So for sigma bond, there will be S and P along the same axis, whereas for pi bond, it will be P only at an angle which is called as Bond angle. Okay. In terms of strength, you can say sigma bond are going to be strong, because now sometimes in material science you have to use your logic also, common sense also. If there is more overlapping, means it is more strong. When there is less overlapping, it is less strong. So definitely sigma bond is going to be more stronger than the pi bond. Rotation of the atoms freely around the bond, okay, because they are overlapping head to head. But in case of pi bond, the rotation is not possible because there are side to side overlapping. Existence, they can exist independently, whereas pi bond cannot exist independently. They will always be present along with other types of bonds also. Hybrid bond, if you talk about, hybrid bonds are formed when the interaction between S and P orbitals occur. Okay, so two different type of orbitals, when they are going to bond together, there will be hybrid bonds. Hybrid bonds are formed when the interaction is between the S and the P orbitals. Relative overlap of the orbitals decrease in the following order. Now this is example. This is important, sorry. This is important. This statement is important. You may get a question. So if you go in this order, then overlapping of the orbitals is going to decrease. So the highest overlapping, it is having the highest overlapping. It is having the highest overlapping. SP, then SP2, then SP3, and the least one, it has the least overlap. Is it clear, everybody? Are you able to follow this? Tell me yes or no in the comment section. Don't lose your patience, okay? Don't become a signum function. You remember this signum function? You must have read it in mathematics. Signum function. It is like this. In the starting, amplitude is very high. As the time goes by, amplitude reduces to 0. So if you prepare, if you read, if you learn, or whatever you do, whatever work you do in your life, if you do in this fashion, you will never get success. You have to have a sinusoidal response. You have to have a sinusoidal response. There will be ups, there will be down, but at the same time, you must, whenever you are high, you should balance it. Whenever you are low, you should motivate yourself. But you keep on moving with the same amplitude in terms of the peak value. I hope you are getting my point. If you want to achieve something great in your life, then you have to do something great in your life. Without doing the great things, you will never achieve or become a great one. Okay, so don't lose patience. I see people are leaving the session in between. This is not a good sign. Okay, if you have a doubt, you are most welcome. You can ask me. So I think it was a good motivation for you. You will understand the importance of consistency. Is it clear, everybody? This was the important point. Note it down if you want to note it. The decreasing order of overlap in the orbitals. Saturated bonds and unsaturated bonds. So whenever there is a single bond, this is called saturated one. Why it is called saturated one? Because the other possibilities are not present. Whereas if you have a double bond or triple bond, these are called unsaturated, because other possibilities are present. So generally saturated bonds are generally more stable. Saturated bonds are generally more stable. We are talking about covalent bonds. Gojo, okay, Mr. Gojo, yes, I can update you. Why we have delayed the second part of ethics, there was a reason. Because today itself we are having the GATE live analysis for civil engineering department. Yesterday also we were having the ESE analysis and instrumentation analysis. So those candidates may be affected, and that is the reason we have planned that tomorrow is 13. So after 13, okay, so next week, Monday or Tuesday, whenever it is possible, we will inform you when we are going to plan the ethics class. But very soon we will plan, very soon. We have already planned it. It is under the process, but because there was GATE live analysis, so we were waiting for the right time so that every student can be benefited. Is it clear, Mr. Gojo? Is it clear? Yes, good evening, Abdul. Listen. So very important point, saturated bonds are going to be more stable and less reactive. Which is more stable, it will be less reactive. Okay. Then the unsaturated bonds. Double and triple bonds are unsaturated, while single bond is saturated bond. Octet rule, I think I have already discussed it, but I have some important point to be discussed in this rule that may be coming in your examination. So please have a look. Now the atoms can combine either by the transfer of valence electron, that is the ionic bond, or it can be the sharing of valence electrons, that is the covalent bond, in order to achieve the octet. Octet means 8 number of electrons in the outermost orbit in their valence shell. This is known as the octet rule. This theory was propounded by Lewis. Okay, Lewis, L-E-W-I-S, Lewis. But there are some exceptions also. Chemistry cannot exist without exceptions. Chemistry cannot exist without exceptions. So exceptions are to the octet rule is, for example, beryllium and boron. Beryllium and boron, they have less than 4 outer electrons. Less than 4 outer electrons, still they are stable. Even if all the outer electrons are used to form the bonds, an octet cannot be attained for these two examples. The octet rule is also broken where atoms have an extra energy level which is close in energy to the p level and may accept electrons and be used for bonding. This is very, very important exception to the octet rule. The second one, okay, take it very seriously. Okay, and the best example for this is PF3 obeys the octet rule, whereas PF5 does not follow. So there are exceptions to it also, octet rule also, okay. Next one. We are defining the number of bonds between the two atoms as how many electrons are shared divided by 2, because we know that 2 electrons are needed to form a covalent bond. So we are saying total number of electrons shared divided by 2, it is going to give you the number of bonds. Usually all the electrons in a Lewis structure are paired. It means 2 electrons will give rise to a bond. If there are odd number of electrons, for example 15 in NO, then there is at least one unpaired electron in the structure, and the such type of material is called as paramagnetic material. We will discuss about the paramagnetic material when we discuss about the magnetism, okay. In the next part, when we are going to discuss the magnetism, then we are going to discuss about paramagnetic materials. So generally these electrons are going to be paired. They will not be isolated. They will not be alone. But in case of the odd number of electrons, there is a possibility of the material becoming a paramagnetic material. Molecular orbital theory. You may get a question from this also. What is this molecular orbital theory? It is a method of determining the molecular structure in which the electrons are not assigned to individual bonds between the atoms, but they are treated as moving under the influence of the nuclei in the whole molecule. So what is happening? We are assuming the transfer of electron, we are discussing the sharing of electrons, but it is not that electron is stationary. Yes, Ritesh, why not? We can plan a general session. Actually, we are planning number of sessions for ESE. First, we will be completing the marathon sessions, because marathon sessions are important. And by that time, we are about to complete the marathon sessions. We will be having number of general sessions for ESE also. But definitely, as you have requested, I will come up with at least 1 or 2 general sessions for ESE also. Okay. So what I was saying, I forgot. Yes. So electrons are not static. Electrons are moving. So how they are actually distributed in terms of a molecule, in terms of a material, that is being explained by the molecular orbital theory. Molecular orbital is a mathematical function which discusses the wave-like behavior of the electron in a molecule. Wave-like. This function can be used to calculate the chemical and physical properties such as probability of electron finding the probability of finding an electron in the specific theory. Let us talk about the 2 types of molecular orbitals which can be formed. The first one is the bonding orbital and the second one is anti-bonding orbital. Okay, two types of molecular orbital. Bonding orbital gives rise to stability, whereas anti-bonding orbitals leads to unstable structure. Bonding orbitals stabilize the molecule because they are between the nuclei. They have lower energy because they are closer to the nuclei. So that is why they are called as bonding orbitals. Whereas the anti-bonding orbitals, in this, the bond forms between the atom is weak and it leads to unstable. They have higher energy because the density of electrons in the orbitals is concentrated outside the bonding region, okay, outside the bonding region, and acts to pull the nucleus away from the other and tends to cause repulsion. That is why it leads to unstable system. How we are defining the bond order? These 2 bond orbitals, they define the stability of a bond formation, and to identify whether the formed bond is stable or not, bond order is defined. How bond order is defined? It is defined as number of electrons occupying the bonding orbitals minus number of electrons in the anti-bonding orbitals divided by 2. divided by 2. Everybody just tell me, are you getting this formula? Say yes or no. Say yes or no. Are you getting this formula or not? Very important. Bond order is defined as number of bonding orbitals minus number of anti-bonding orbitals is stable minus unstable divided by 2. So whenever your bond order, listen very carefully, whenever your bond order is going to be greater than 0, what does it mean? Whenever your bond order is going to be positive, what does it mean? It means the number of bonding orbitals is more than the number of anti-bonding orbitals. So it is going to be stable. Are you able to understand? Are you able to follow this? How you are defining the stable or unstable? Now let us talk about the third important primary bond, that is metallic bond. As the very name indicates, metallic bond is going to be formed between the metals, yes or no? Now, why we are defining metallic bonds separately? It is for that reason, if you talk about metals, metals have excess of free electrons, yes or no? Hello? They have excess of free electrons, and that is the reason why metals are such a good conductor of electricity and heat, because they have excess of free electrons. So if you see from the microscope the structure of metals, you will see there is a positive center which is surrounded by an electron cloud, and this electron cloud is so dense because number of free electrons are very high that it's like a sea of electron. An electron is moving, it is not stationary. Are you getting this? So it looks something like this. Something like this. You can see the sea of electrons. Can you see? Minus, 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 minus. Every positive surrounded by so many minus, minus, minus. So these electrons can transfer or can go from one point to another point very easily, and that is why metals are a good conductor of heat and electricity. So metallic bond is the term used to describe the partial sharing of valence electrons by the neighboring atoms. Partial sharing. Why partial sharing? Because so many electrons and they all moving. Hello? So that is the partial sharing. Are you getting this? It's something like this. So let me show you. Suppose I use the green color to show you the electron cloud. So for this positive, it is going to be something like this. Something like this. So it is very difficult to know which electron is getting shared with which atom. Tell me in the comment section, are you able to follow this? Hello? Not getting any response. If you like the content and if you are able to understand and follow me, so do not hesitate to tell me in the comment section. Tell me, are you able to follow me? Are you getting some confidence? Okay, let's move on. So, metal bonding constitute the electrostatic forces of attraction between the delocalized. Every time delocalized means electron is not stationary. Here and there, here and there, here and there, because so many electron clouds, it's a sea of electrons. And positively charged metal ions. The examples are metals, aluminium, magnesium, copper, so and so. Okay, thank you everybody. Thank you, Mr. Witcher. Interesting name. So now finally you can have a little comparison of ionic bond, covalent bond and metallic bond. If you see, Ionic bond is going to have low conductivity. Remember salt. Remember salt, rock salt. Covalent bond, medium conductivity. And metallic bond, high conductivity. Ionic bond, non-directional in nature. Covalent bond, directional in nature. And metallic bond, non-directional in nature. Ionic bond soluble in the water. Always take the reference. Always take the reference. Okay. For ionic bonds, you can take the reference of salt, NaCl, the best example. So, salt is soluble in the water or not? No, sorry, yes, it is soluble in the water. Whereas, if you talk about covalent bond, it is not soluble except in benzene, Metallic bond, not soluble. Again, metals, it is very difficult to dissolve. Examples for ionic bond, NaCl, MgO. Covalent bond, diamond, silicon, germanium, etc. Metallic bond, aluminium, copper, magnesium, etc. Is it clear, everybody? See the next. Yeah, there are some comparisons we want to do, and I will tell you some trick so that you can remember each of this. Okay, there may be some questions and you will feel confident. So this is the one of the most important slide. So I will give it 7 stars. Twinkle, twinkle, little star, how I wonder what you are. So if you talk about the bond strength, in terms of bond strength, ionic bond is the strongest one. Then comes the covalent bond and then metallic bond. Melting point, again, ionic bond has the highest melting point, then covalent bond, then metallic bond. Boiling point, ionic bond has the highest one, then covalent bond, then metallic bond. Conductivity, now metallic bond is going to have the best of the conductivity, then ionic bond, then covalent bond. So if you see out of these 3 parameters, ionic bond is going to have the first place, covalent bond at the second place, metallic bond at the third place, but for conductivity, it is going to be changed. So this is how you can remember it. Now let us talk about the secondary bonds. Yes, very important question asked by Kalp, where you will be getting the PDF of this session. So PDF of this session you will be getting in my personal Telegram channel on BYJU'S Exam Prep, that is Electrical by Ashutosh Saxena. Electrical by Ashutosh Saxena. Just open the Telegram app after the session, search by my name, that is Ashutosh Saxena, Electrical by Ashutosh Saxena, and you will be getting my photograph. You can join that channel. Just after the session, I will be uploading it. Okay. Now we are starting with the secondary bonds. So first we are talking about hydrogen bonds. When hydrogen and oxygen atoms are covalently connected, a specific kind of dipole bond is developed, which is called as hydrogen bond. So hydrogen bond is like a dipole bond, okay, and it is covalently connected. The oxygen atoms have the higher affinity. The oxygen atoms have the higher affinity for electrons. So definitely the electrons are going to be shifted towards the oxygen for the shared electrons pair than hydrogen atoms, and that is the reason the shared electron pair shifts towards the oxygen. The example is water, ice, ammonia and H2S. Is it clear? Hydrogen bond. So the best example of hydrogen bond is going to be water. Then we have, yes, hydrogen bonding. This angle is somewhere around 104. Okay, you can cross check it. This is 104 degrees. 104 degrees. 104 degrees. Okay. Next one is the various properties of hydrogen bond. Solubility. Lower alcohols are soluble in the water because of the hydrogen bonding. So solubility is because of hydrogen bonding which can take place between water and the alcohol molecule. So I think every person who is fond of this experiment, he must be knowing this. Abhishek is asking what is the meaning of affinity. Affinity is the property of any atom so that it attracts the negative electrons towards it with a force. So chlorine atom is having, oxygen atom is having, like chlorine is also having higher affinity. Okay. The simple meaning of affinity is closeness. Okay, in the most crude terms you can say it is attraction, closeness. So electron affinity means how much you can say there is a tendency towards that. If the pair of electron is shared, then that electron is shifted towards the atom which is having higher electron affinity. Is it clear, Abhishek? Now volatility as the compounds involving hydrogen bonding between different molecules have a higher boiling point, so they are less volatile. So molecules having hydrogen bonding, they are less volatile because of hydrogen bond, because they have a higher boiling point. Important, you should remember. Viscosity and surface tension. I hope you understand what is viscosity. Okay, the friction between the two layers of a fluid is called viscosity. If viscosity is high, then the flow is not going to be much and it is going to be non-uniform. Okay. The substances which contain hydrogen bonding exist as an associated molecule, so their flow becomes comparatively difficult because viscosity is high. So they have higher viscosity and higher surface tension. I hope you understand surface tension. Okay, intermediate. So simply you understand surface tension is high, viscosity is high, volatility is less because boiling point is high, and solubility is high. Okay, because of the hydrogen bonding. Now the most popular one, Wonderwall's bond. Wonderwall bonds, it exists between the covalently bonded molecules when there is no valence electrons available to form the primary bond. So when the primary bond is not possible, then Wonderwall bond is developed. Wonderwall forces are weak. That is why Wonderwall bond is also weak. They are weak intermolecular forces that are dependent on the distance between the atoms and the molecules. These forces arise from the interaction between the uncharged atoms or the molecules. The example is hydrogen bonding. So hydrogen bonding is also example of van der Waals bonds. Then we have dispersion bond, dispersion forces. Then we have dipole-dipole interaction. So we have dipole bonds also. Let us talk about the dispersion bond. What is the meaning of dispersion? You understand? What is the meaning of dispersion? Suppose this is the nucleus and these are the electrons in the various orbit. So if something is, if everything is okay, you will say the center where nucleus is there, the center of electron cloud is going to overlap with the nucleus. If everything is okay, everything is uniform, everything is, you can say, perfectly okay. But practically, it is not possible because of so many reasons. There may be n number of reasons because of which the center of the electron cloud will get shifted with respect to the positively charged nucleus. And this shifting is called as dispersion. And this gives rise to a particular type of bonding which we are calling as dispersion bond. So dispersion bond, when the electrons in a symmetrical molecule are evenly dispersed around the nucleus and rotate continuously around it, the center of positively charged nucleus and the center of negatively charged electron cloud is going to coincide. So there is no problem. But second case, in molecules where the distribution of electrons is not symmetrical. So when the distribution of electrons is not symmetrical about their nuclei, then dispersion bond will come into the picture. This causes the displacement between the center of positive and negative charge centers. Okay. And it is going to be a weak interaction between the two molecules. It will be a weak interaction. It's created by the dispersion effect. I told you what is dispersion effect. And this bonding is known as dispersion bond. Dispersion bonds are found in the noble gases. Helium, neon, argon, krypton, xenon, radon. You remember that? Periodic table. Yes or no? So argon, helium, neon, all them, they have dispersion bonds. So understand this center of positive charge nucleus, negatively charged electrons orbiting in different orbits, and the center of positive charge and the negative charge is coinciding. But because of dispersion, if the electron cloud is not that uniform, then there is a gap, there is a displacement between the positively charged nucleus and the center of the negatively charged cloud, and this is called dispersion. This displacement is called dispersion. Everybody just tell me in the comment section, are you able to follow this? Understand what is dispersion? Dipole bonds. Now, dispersion you can understand like this, dipole is going to be like this. Same thing with a great effect. Unequal sharing of electrons creates the positively charges on the molecules. It is unequal sharing. As a result, permanent dipoles are developed. These dipoles attract each other. Yes or no? The positive will attract negative, the negative will attract the positive of other one. So, these dipoles will interact each other and thereby forming dipole bonds. Dipole bonds are stronger than dispersion bond. Definitely it has to be. Dipole bonds you are talking in terms of the dipoles at the ion level. Dispersion bond you are talking about the atomic level. Displacement between the center of positively charged nucleus and the negatively charged electron cloud. So, dipole bonds are stronger than dispersion bond, but they are less strong than primary bond, because primary bonds are going to be quite strong. The examples can be hydrogen fluoride. Examples can be hydrogen fluoride. You see hydrogen, and this is fluoride. Again, halogen, 7 electrons in the outermost. So, this will share 1 electron like this. And because of unequal sharing, there will be some positive charge here, some negative charge here, and it will develop a dipole, and it is going to attract or repel the other dipoles. So, there will be dipole bonds. Now, what are directional and non-directional bonds? Directional bond, in this bond, the bond strength is unequal in different directions. So, bond strength is going to be different in different directions. It is dependent upon the direction or the sense of direction in which the bond strength is measured. So, we will be having the directional bond. Non-directional bond, in this bond, the bond strength is equal in every possible direction. There is no difference. So, it is non-directional. How you see the difference between the directional bond and the non-directional bond? Directional bond, so covalent bond and hydrogen bond are going to be the directional bond, and except it, all other are going to be non-directional. Ionic, metallic, Wonderwall. Directional bond are formed at a specific angle. For example, you remember when I gave you the example of hydrogen. So, it was something like this, O minus, H plus, and the angle was a specific 104 degrees. So, they are formed at specific angles, whereas non-directional bonds, they are not formed at a specific angle. Directional bond, overlapping electron orbitals are directionally oriented, whereas overlapping electrons orbitals are spherically symmetrical. So, they are symmetrical, that is why they are non-directional. Is it clear, everybody? Let us see the difference between the dipole bond and dispersion bond. Dipole bond and dispersion bond. Dipole bond, they are stronger. I told you, if dispersion bond is like this, dipole bond is like this. So, you understand this. They are weak compared to dipole bonds. Dipole bond, there the secondary forces of attraction arise during the bonding, whereas dispersion bond, it is the momentary polarization. It happens for some time and it may go also. It may go also. It happens and it may go. It is because of unequal sharing of electrons. It is because of the displacement between the center of positively charged nucleus and the negatively charged electron cloud. Examples of dipole bond: hydrogen, you can say water, H2O, and hydrogen fluoride. For dispersion bond, we have the inert gas crystals. I hope it is clear. So now we'll be starting the crystal structure. Everybody, tell me till now how you are feeling. Are you getting some confidence out of it, the discussion we are having? I don't see the comments. Just give me one moment. Yes, everyone. So I hope at least you are getting something. So now we'll be starting the crystal structure. Now please understand, when we talk about solid, we talk about the solid material. Crystal structure is one important way of understanding that how different materials are going to exhibit different unique physical and chemical properties. How atoms are arranged, that will give unique features, unique properties to different materials. And the study of this regular or irregular pattern or the arrangement of atoms in a material is defined as crystallography. Is it clear? So crystal structure we are defining as it is obtained by attaching atoms to atoms and group of atoms and molecules. Okay. So like you construct a building, you construct a house. How you construct it? Brick by brick, brick by brick. That is how you construct a material, atom by atom, atom by atom, atom by atom. Then crystal structure is the description of the ordered arrangement of atoms, ions or molecules. Now when you construct a house, there is a certain pattern which you have to follow. Yes or no? So one brick you are using here, one brick here, then on the joint you are putting another layer of brick. Why? To make it more stable. Have you seen the construction of a house or a building or a wall? Why they are doing like that? To make it more stable. The same thing is happening here. In a crystal structure, the atoms are going to be arranged in such a way so that you get the most stable system. Yes or no? Then, what is crystallography? I have just told you. It is a branch of science which is concerned with the structure and properties of crystal. Crystallography is the experimental science of determining the arrangement of atoms in a crystalline solid. Solids you can define in terms of two classifications. Number one is crystalline solids, crystal formations, and non-crystalline solids, non-crystalline formations. Okay, so I will give you some very weird example, but for that is only for the reason you will always remember it, you will never forget it. When you say crystal, it means there is a regular repeated pattern, well arranged. Something like the VIP colonies. where various big political leaders, affluent people, they used to live. Have you seen those colonies? Some of you may belong to that category also. If you go to a very, you can say, rich colony, you will see the houses are arranged in a very proper manner. Everything is good. Everything is at the right place. Non-crystalline, it's a mess. There is no regular repetition, no pattern which is followed. It is random. So it's like a slum area. Okay. Please forgive me the word I am using, but it will tell you that how real life you can relate with the technology and you can remember it. There is no orderly pattern. There is no orderly pattern. Are you getting this? Next. So crystalline solid, how we are defining, the atoms are going to be packed in a very regular, periodic fashion. Okay, regular and periodic. If you are standing here, A point, then all around you the environment is same. If you are standing here, then also all around you environment is same. So this is crystal structure. Okay. So definitely it is going to have high density. They have sharp melting point and slow cooling rate. Why there is a sharp melting point? Why there is a sharp melting point? Because there is a regular repeated pattern. So the atoms are well arranged. They are very stable, very strong. So they will not just start melting slowly. No, they will not melt. They will not melt. But when the temperature goes higher than the melting point, then suddenly they will melt away. So they have sharp melting point. Then slow cooling rate. The same way reverse you can apply. So they have slow cooling rate also. Crystalline solids you can define into two ways. One is single crystalline solids and polycrystalline solid. Again, I am giving you a very weird example. Please forgive me. Single crystalline solid is going to be people living in the rich colonies. Very much order is there. Very much order is there. Polycrystalline is like the middle class basti. So if your single crystalline is like this, I am trying to make it uniform, okay? Then the polycrystalline, it is going to be something like this. There will be certain regions, something like this. Now this is going to have another pattern. This is going to have another pattern. This is going to have another pattern. Another pattern. Another pattern. I'm just trying to make you understand, otherwise it will take more time. So polycrystalline means, okay, so I got the first heart and love from Mr. Gaur Kranti Kumar. Thank you so much. I was requesting for at least some amount of love, but I was not getting. No problem. It happens with me very regularly. Okay, so crystalline means there is a regular repeated pattern, well arranged, no problem. But if you go to the polycrystalline, this is also crystalline, but it has regions. Within that regions, there is a regular pattern followed. But different regions are going to have different you can say, order and arrangement of atoms. Are you getting this? Thank you all. So single crystalline solid we are defining as it is the periodic and repeated arrangement of atoms, almost perfection. There is no break in the atomic order. No break in the atomic order means whatever you see here, you will see the same thing here, you will see the same thing here. It is going to be same. Thank you so much, Jeevan. Thank you. I was just joking, don't worry. Examples can be for crystalline. It can be sugar crystals, it can be gems, etc. Polycrystalline solids, what can be the examples? For example, rocks and ice. So polycrystalline, it is composed of many small crystals or grains with different crystallographic orientations. So crystallographic orientation, I hope you understand, in terms of arrangement of atoms. Then there exists some atomic mismatch within this within the region where two grains meet. This is called as grain boundary. So this was the grain boundary. So this was the grain boundary. This is the grain boundary. This is a grain boundary. This is a grain boundary, like this. Okay. Grain you understand in terms of the atom. So it is little slow, no problem. Non-crystalline solid, when the atoms are packed in the random manner, there is no order. So definitely there will be low density. Yes or no? Crystals, it is going to be closely packed. It is not closely packed, so low density. Slow melting point and fast cooling rate. Slow melting point and fast cooling rate. Let us talk about isotropy, anisotropy and orthotropy. Okay. Isotropy, anisotropy and orthotropy. Isotropy. Isotropic substances means where the various properties are not dependent upon the direction of observation. Whatever direction you observe, that property is going to have the same characteristic. So substances for which the physical properties are independent of the direction of measurement or observation, those materials are called as isotropic materials. Isotropic materials. Understood? Examples: gases, liquid, amorphous, okay, solids are isotropic. Anisotropic. Anisotropic is the complete reverse of isotropic. When the various physical properties are dependent upon the direction of observation, that is anisotropic. So properties are dependent on the direction of measurement, they are called as isotropic materials. Examples are elastic modules and refractive. I think there is some problem. Okay, so they are giving the examples of the properties. Okay, properties, not the material. Orthotropy, when the properties are identical in some direction, for some region it is identical and for other parts it is not dependent. So for some when properties are identical in some direction and dissimilar in other, then it is known as orthotropy. This is important. For example, the unidirectional fiber composite. Unidirectional fiber composite. Is it clear, everybody? Now, polymorphism and allotropy. Some metals as well as non-metals. Okay, some metals as well as non-metals, they have more than one crystal structure. Polymorphism. Morph means shape or form. Poly means many. So when a material can exist in many physical forms, okay, more than one crystal structure, then it is known as polymorphism. When the property of some chemical elements to exist in two or more different forms in the same physical state, this is known as allotropy, allotropes. Okay. The crystal structure depend on both temperature and pressure. Definitely it has to be. This polymorphism and allotropy is found in carbon, ice, tin, etc. So many other examples can be there. So now I will be discussing some very basic points about the crystallography, which are very important, very direct, and maybe asked in your examination. Every year you are getting at least, almost every year you are getting one question from what I am going to discuss now. Lattice point. What is the meaning of lattice point? Have you seen a large apartment building? Have you seen a large apartment building? So when the building is constructed, pillars and the structures are first placed. Yes or no? Then walls are erected. So this structure, this is called as lattice. This is called as lattice. And all these cross section points They are called as lattice points. They are called as lattice point. Is it clear? Everybody just tell me. You're not commenting. You guys are very lazy, lethargic. Okay? Be active in the comment section. Okay? I hope you are getting this. Apart from this lattice point, we have basis also. Basis, or it is called as motif. Basis or motif. What is this basis or motif? Now this lattice point, there can be so many lattice points, yes or no? Hello? There can be so many lattice points. But it is not 100% sure that every lattice point atom will be present or not. It is not 100% sure. Atom may be present, atom may not be present. Hello? I hope you are getting this. What I'm saying is, all these lattice points are there. But whether atoms are present on these lattice points or not, there is a different possibility. Now, those lattice points where atoms are present, atoms may be present like this. Suppose only one atom is present. Or you say 2 atoms are present. 4 atoms are present. I am just giving you one random example. Hello? So, this basis or motif, when it is repeated in the 3-dimensional lattice array, you get the material. I hope you are getting this. Are you getting the difference between lattice? This is also called as a space lattice. Are you getting the basic idea? Is space lattice or lattice? What is the lattice point and what is basis and motif? This structure is called lattice. The crossover points, they are called as lattice points. All these lattice points, it is not necessary that atoms will be present. May be present, may not be present. But if atom is present, it may be 1 atom, it may be 2 atoms together, it may be 3 atoms. That is called as basis or motif. I hope it is clear now. So how we are defining the lattice point? In a crystal lattice, each atom molecular ions is represented by a single point. So all these points are called as lattice points. These points are called as lattice site or lattice point. So a space lattice already I have explained. Understood? Are you getting this? Space lattice already I have explained. And it is a 3-dimensional one. It is I have shown you in terms of 2 dimension, but it has to be 3-dimensional, okay? So crystal we are defining in terms of the 3-dimensional periodic arrangement. You can say repeated regular arrangement of atoms, that is called as crystals. Unit cell. Unit cell is the fundamental unit. Unit cell is the fundamental unit of your crystal, which gets repeated in the 3-dimensional space in a regular repeated fashion. You will get the whole crystal. Are you getting this? For example, this is my crystal. I want to know what is the arrangement of atoms. So, listen very carefully. Suppose the arrangement of atom is like this. Arrangement of atom is like this. So, there will be a 3-dimensional regular repetition of this arrangement. So, why I will go for the repetition? I am only interested in this one. So, this one is your unit cell. The most fundamental unit which when repeated periodically, regularly in the 3-dimensional space in all possible directions, you will get the material. I hope you are getting this. Everybody tell me in the comment section. Now we have primitive and non-primitive unit cells. How we are defining the primitive and non-primitive unit cell? Primitive cell, when the lattice points, actually it should be when the atoms are present only at the corners, then it is primitive cell. When atom is only present, Because lattice point atom may be present, may not be present. Hello? Are you getting the difference between space lattice, lattice point and basis or motif? If you don't understand this, you will not understand anything. This is my guarantee. But if you understand this, I can tell you with possibility that you will understand the rest part of the discussion also. But this very fundamental thing you must understand. I have given a very beautiful example in terms of the tall tower or building structure. When it is constructed, have you seen? There are large pillars, beams. Hello? Are you able to follow this? So that structure is your space lattice. And every intersection point, crossover point is your lattice point. But that lattice point, atom may be present, may not be present. If atom is present, one atom is present, two atom present, three atom, how many atoms present? That is your basis or motif. I hope you understand that. Non-primitive cells, they are defined as when the atoms are present apart from the corners also. Maybe on the face of the unit cell, maybe on the center of the unit cell, maybe on the top or bottom side. Yes or no? Any possibility may be there. So when atoms are present at the corners as well as at some other point, then it is called non-primitive cell. Lattice parameters. Lattice parameters can be defined in terms of the axis. For example, x-axis, y-axis and z-axis. Then intercepts. Intercepts means the intersection along the x-axis, intersection along the y-axis, intersection along the z-axis. So it may be A, B and C. Then we have interaxial angles. Interaxial angles. These interaxial angles can be alpha, beta or gamma. Alpha, beta or gamma. Depending upon the various possibilities in terms of the arrangement of atoms so that you get a stable structure between A, B, C and alpha, beta, gamma, you get various possible space lattice. And those lattices are called as Bravais lattice. Mr. Bravais gave us the 14 most standard lattice structures which are possible. Actually, he has given a very large number, but out of them, 14 are fundamental. So if you talk about the Bravais lattice, okay, as I told you, basically there are, the standard one is 14. Okay, I will not go to the depth of all these because it is very easily available in various books or something, because this is a marathon session. We have to complete so many things, otherwise it will take another half an hour. So it is better just after the class you go to any of the standard book you have, or even on the internet also. If you type Bravais lattice, you will get all the structures, their relation, you can follow it. What is coordination number? Very important to understand. Coordination number define various other physical chemical properties of the material. It is the maximum number of atoms which are directly in contact with a particular atom. In any material, in the unit cell, there is one atom which is important, which is unique. So the maximum number of atoms which are in direct contact with that atom, that is defined as the coordination number. It is defined as the number of nearest neighboring or touching atoms to each other. Atomic packaging factor. What is atomic packaging factor? I will give you a very simple definition. Suppose you have a bucket. Can you have a bucket? Can you have a bucket? Yes, you can have. Suppose this is a bucket. Okay, this is your bucket. And I give you some balls. I give you some balls. I give you some balls. So you will drop the balls one after the other, one after the other, one after the other, till the bucket is completely filled. Till the bucket is completely filled. Now I am asking you, how much percentage of volume, of this bucket is being occupied by the balls? So what you will do? Listen my words very carefully. Never ever in your life you have to even revise it. You will first count the number of balls inside the bucket, and if the balls are symmetrical, you will find the volume of one ball, number of balls inside the bucket multiplied by the volume of one ball, that will be the total volume occupied by the balls, and divided by the total volume of the bucket, multiply by 100, you will get the atomic packaging factor. And that is nothing but atomic packaging factor. The volume of the unit cell in the denominator. In the numerator, the total volume of the atom present in the unit cell. Multiply by 100. So it is basically, you can say, atomic density. It is basically the atomic density. Yes or no? It is the ratio of the volume of the atoms in a unit cell to the unit cell volume. So the various Bravais lattice possibilities I am mentioning here, I cannot go into much deep because of the time limitation. After the session, you can read about it. So we have cubic. In the cubic, all the ABC intercepts are of same size, and interaxial angles alpha, beta, gamma all are equal and equal to 90. Then we have hexagonal. The name itself tells you that all the intercepts cannot be same. So A and B are same, but C is different. C is the height of the hexagonal, so it is different. Alpha and beta are 90, and definitely gamma has to be 120 degree. You see, between the hexagonal, two sides of the hexagon, what is the angle? The angle is 120 degree. Then we have tetragonal. Tetragonal, A and B same, but C is different. A and B same, but C is different. But the interaxial angles are all 90 degree, alpha, beta, gamma 90 degree. Rhombohedral. ABC same, but alpha, beta, gamma same, but not equal to 90 degree. Orthorhombic. Neither of the sides same, intercept same, ABC different, but all angles are 90 degree and similar, same. Monoclinic, ABC different, alpha and gamma same 90 degree, beta different. You have to remember it, okay? There is no shortcut that you can, okay? You see it, observe it, you see the actual diagram in your book, you will recall it, okay? It will take some time for you to observe this. I cannot give you a tablet that eat it and you will remember it. Then you have triclinic. Sides different, all angles different other than 90. You have to remember it. Let us talk about the first one, that is the simple cubic crystal structure, which is in short called as SCC, simple cubic crystal structure. Now in this there are, if you talk about a cube, so in a cube there are 8 corners, so every corner there will be one atom present. So in this structure, 8 corners of a cube are occupied by 8 atoms. For example, polonium, fluorspar, manganese, etc. So you see this cube. At each of these corners, one atom is located. One atom is located at the 8 corners. 1, 2, 3, 4, 1, 2, 3, 4. If you talk about the number of atoms in the simple cubic crystal structure, you will understand what is the contribution of each of these atoms. It is going to be 1 by 8. Okay, it is going to be 1 by 8. So if you talk the effective number of atoms in the unit cell, then it is going to be 1 by 8. Just a moment. Yeah, it is going to be 1 by 8. That is the contribution of one atom. How many such atoms? 8. So 1 by 8 into 8 is 1. Something like this. Now if you want to relate the intercept of the unit cell dimension and the radius of the atom. Now you see the atoms are going to be in contact like this. Yes or no? Atoms are going to be in contact like this. So if you observe there, this is the radius r. This is radius r and this A is the A intercept. So very easily you can write A is equal to 2r, or radius of the atom you can write as A by 2. That is the dimension of unit cell. Intercept along the x-axis, y-axis or z-axis. What is the coordination number? Very easily you can observe. Suppose you talk about yes, suppose you talk about the one corner. Suppose you talk about the one corner of the cube. So if this is the corner cube, one atom, another atom, another atom, another atom. So how many are them? How should I make you understand? Yes, suppose you focus on this one. Suppose you focus on this one. So within one unit cell, it is directly in contact with this one, and this one. I hope you understand this. So 3 atoms within one unit cell and such 3 atoms with the nearby unit cells. So total it is going to be 6. Total it is going to be 6. Is it clear? If you are not able to understand it, you can draw the complete diagram, but it will take some time. So I hope you understand. If this is the, let me use another color. So if this is the case, now suppose I am talking about this corner atom. I am talking about this corner atom. So this corner atom will be in direct contact with this one, and this one. Similarly, there will be 3 other. So total 3 plus 3, 6. Now I hope you understand. So what is the coordination number? 6. How we are defining the coordination number? The number of atoms, maximum number of atoms which are in direct contact with a unique atom, neighboring atom, total coordination number. Atomic packaging factor, how you are defining? It is the volume of the atoms in a unit cell divided by the volume of the unit cell itself. Yes or no? So we are defining it as sum of the atomic volume in a unit cell divided by the volume of a unit cell, and is the total number of effective number of atoms inside the unit cell. That is 1. 4 by 3 pi r cube, because atom we are assuming to be spherical. So the volume of the sphere. Now the volume of the unit cell is going to be a cube, because it is a cube and side is going to be a. And A is 2R, just put it here. If you solve it, you will get 0.52. Atomic packaging factor for the simple cubic structure is going to be 0.52. Everybody just tell me yes or no. Okay, so I think this is body-centered cubic. This is body-centered cubic. So this is in short called as BCC. So every corner is again having one atom, but there is one extra atom sitting at the center of the cube. Okay, something like this. Examples are chromium, tungsten, vanadium, molybdenum and sodium. You see, all the 8 corners is occupying one individual atom, and at the center there is one extra atom. Now this extra atom is going to be the unique atom. This extra atom is going to be the unique atom. What is the total number of effective atoms? So the atom which is at the center, it has the 100% contribution, yes or no? So it is going to be 1 by 8 into 8 for the corner atoms plus 1, that total atom inside the unit cell, so it is 2. What is the relation between the radius and the unit cell dimension? Now understand this. When you talk about the body-centered cubic BCC, very important point I am writing, atoms are in contact along the body diagonal. Along the body diagonal. Listen very carefully. Listen very carefully. It is something like this. Okay, something like this. What is the body diagonal? I'm going to draw it. Please, if you can observe. This point and this point is called the body diagonal. We are saying atoms are in direct contact along the body diagonal. So if the atoms are in direct contact along the body diagonal, please understand this. I want to know what is this distance. I want to know what is this distance. Can you tell me what is this face diagonal? Because this is A, this is A, this is A. What is this? Root 2A. This one is the face diagonal, bottom one. This is A square plus A square under root 2A square under root, so root 2A. This is root 2A, this is A. What is this? Square of this, square of this. 2A square plus A square, 3A square. So it becomes how much? 2A square plus A square, 3A square. So under root 3A. Hello, are you able to follow this? And along this body diagonal, how atoms are going to be arranged? Along this body diagonal, how atoms are going to be arranged? See very carefully. One atom at the center, one atom at the corner, one atom at the corner. So this is R, this is 2R, this is R. So total 4R. So can I write 4R is equal to under root 3A? Can I write this? So under root 3A is equal to 4R, or you can say R is root 3A by 4. Either you remember it or you understand it. It's your choice. What is the coordination number? Very interesting for body centered cubic. What is the unique atom sitting at the center of the cube? So coordination number is going to be 8. Atomic packaging factor. How many effective number of atoms present? 2. So 2 into 4 by 3 pi r cube divided by A cube. What is A? 4R by root 3. Simplify it. You will get 0.68 as the atomic packaging factor for the body centered cubic. Is it clear, everybody? Is it clear? Say yes or no. You're not saying anything. I don't know why. You guys are not commenting. Then we have, okay. So this is face centered. This is face centered cubic. Face centered cubic. FCC. Face centered cubic means apart from the 8 atoms at the 8 corners, there will be atoms present on the faces also. How many faces are there in a cube? 6. 1, 2, 3, 4, top and bottom 6. Okay. For example, nickel, aluminum, copper, silver, gold, platinum. So you see all the 8 corners, 1, 1, 1, 1, 1 atom, and all the faces, top, bottom, 1, 2, 3, 4. Okay, like this. What is going to be the number of effective atoms? So for the atoms at the face, the contribution inside the unit cell will be 50%. Okay. So it is 1 by 8 into 8 for the corners and 1 by 2 into 6 because 50% contribution. So it is 1 by 2 and 6 faces are there, 6 atoms are present. So total it is 4. Total it is 4. You can see this. One interesting part of this FCC is that atoms in contact along the phase diagonal. What does it mean? You see the face. Atoms are in contact along the phase diagonal. This is 2R, this is R, this is R. So total it is 4R. Now this 4R will be equal to what? This is A, this is A. So it is root 2A. You cut it, it becomes 2 root 2. So R becomes A upon 2 root 2. I hope it is clear. Coordination number is very interesting for FCC. Coordination number is very interesting for FCC. How to attempt pre? You just go to the examination center. Okay, take the question paper, solve it, put the answers in the sheet. How much you are getting, that is the only thing you have to do. See, just 10 days before you cannot ask this question. Are you getting how serious I am for this question? There is nothing left for us to do. Are you getting this? But next year definitely you can do wonders if you have that commitment and desire. There is a difference between desire and commitment. Everybody is having desire without any commitment. But if you have a desire also and a commitment also, then you can do it. I hope you understand, Mr. Visher. So it is going to be quite interesting. I will ask you to focus on this atom at the face. This is the unique atom. So within the same plane, how many atoms it is touching along the face diagonal? 1, 2, 3, 4. Yes or no? So this is 1, this is 2, this is 3, this is 4. But apart from this, there are other 4 faces. Top, bottom, side, side. They are also in contact. So 5, 6, 7, 8. But this is only the left hand side. What about the right hand side? Right hand side again 9, 10, 11, 12. So what is the coordination number? 12. Is it clear, everybody? Is it clear, everybody? Say yes or no. Atomic packaging factor. How many number of atoms were present? 4. So it is 4 into 4 by 3 pi r cube divided by a cube. Put the values, it is 0.74. Atomic packaging factor of the face centered cubic. Then we have hexagonal closed packing structure. Okay. Please understand, hexagonal closed packing structure is different from hexagonal. Hexagon. Are you getting this? Why? Please understand. At every corner, the base, top and the base, bottom and the top and the bottom, they are hexagonal. They are hexagonal. Okay. So how many faces are there? 1, 2, 3, 4, 5, 6. Plus top and bottom, 8 faces are there. How many corners? Hexagon. So 6 corners on the top, 6 corners on the bottom. How we are defining the hexagonal close? You must say HCP, hexagonal close packed structure. So top and bottom hexagonal. How many corners? 12. All the 12 corners, there will be one atom present. All the top and bottom together, 12 corners, one atom will be present. One atom at the center of bottom and one atom at the center of top face. Top and bottom face, one atom at the center. But there are 3 unique atoms inside the unit cell. 3 blue one, 3 atoms inside the unit cell. This is hexagonal closed pack structure. The examples are zinc, cadmium, beryllium. Okay. What is the effective number of atoms? Now the atoms which are at the corners, 12 corners, their contribution is going to be 1/6 for every individual atom. From the angle relation you can find it, but don't need to go into that mathematics. That is a mathematical part. We are not interested much in that. So 1/6 into 12, 12 atoms at the 12 corners. Every atom at one corner contributes 1/6 plus 1/2 into 2, the top and bottom face atoms at the center, 50% contribution, 1/2 into 2, and 3 atoms inside the unit cell plus 3, so total it is 6. Total it is 6. Sorry. The unique atom is going to be this one, at the top or the bottom of the phase center. So there will be 3 atoms here in direct contact. There will be 3 atoms here. So total coordination number is 6. Sorry. Anything? Okay. There are 6 corner atoms also, na? 3 here, 1, 2, 3, 3 here, 1, 2, 3, 4, 5, 6, 7. What is the wrong? Sorry. 3, 3, 6, 7, 8, 9, 10, 11, 12. Okay. Same phase, there are 6 corners atoms. 3 above, 3 below. So total 6 plus 3 plus 3, 12. Diamond cubic structure. Now in this something you have to remember. It has sp3 hybrid covalent bond. The bonds are directional in nature and the bond angle is 109.5. Okay, this is very standard one, so you can remember it. The space lattice of the diamond cubic is face centered cubic, FCC. Very important point, you must remember it. Just a moment. Now you must remember that diamond is having tetrahedral, something like this. How we are defining tetrahedral? Something like this. Sorry. So it is something like this. I hope now you understand. This is called tetrahedral structure. Okay, Mr. Witcher, very lengthy. I am 2022 pass out. I got the offer letter from a company, did my training in my final year. After that, they never sent me onboarding period. So in October, I started preparing for GATE. So no problem. See, no problem. I tell you one thing. The same thing happened to me also. In my BTech, I got 3 placements. Okay. And that was the time when there was global economic recession. In recession itself, I cracked 3 jobs. But none of the job, they gave me the final offer. I got the offer letter, salary structure, everything was discussed. But still, finally, I did not got anything. But that is a very small thing. First thing you understand, there is nothing permanent. What you are having, that is also not permanent. What you will have, that will also be not permanent. So why you are worried about it? You understand the difference between the stagnant water and the flowing water. If you stagnate yourself, if you stop at one point, you will not grow. What happened, happened. Let it be. You can't change it. You can't decide it. You can't decide things which are not in your hand. You can decide things which are in your hand. Can you decide when it rains outside? No. So what is in your hand? You better take an umbrella. You should be the driver of your destiny, not others. Okay, I hope you are getting the idea. There is nothing called losing. It's just a learning experience. That's a good thing. That's a good sign. Then you should be motivated. Even after so many mishappenings, still you are standing and fighting. So I wish you all the best, and I hope next year you will be in a very good situation. Okay, Mr. Vijay, I don't know what is your real name. Join us, my Telegram channel. We'll discuss what we can do together. Okay, so what I was discussing, tetrahedral structure. Number of excuse me, number of atoms in the diamond cubic structure, I would suggest you to just remember it. It is 1 by 8 into 8, 1 by 2 into 6 because it is face centered, 8 atoms at the 8 corners, and 1 into 4 because of that tetrahedral structure. It's okay, don't say thank you. So it is 8 effective number of atoms. Now let us talk about the Miller indices. Miller indices are basically used to identify a particular plane in the crystal structure. Are you getting this? To identify a particular plane in the crystal structure, we are using the Miller indices. Miller indices we are defining by using the symbols HKL, HKL, okay. And how we are defining this Miller indices, I will tell you. So HKL, if this is the bracket, there is a significance of this bracket, then it denotes a plane. When it is this big bracket, okay, then it denotes a direction. And when it is the middle bracket like this, then it denotes a family of planes. So you should have this reference in your mind, okay. And when it is written like this, less than or greater than sign like that, then it denotes a family of directions. Now let us understand the step, how Miller indices are going to be formed. Now what you have to do is, suppose you are saying P is the intercept along the x-axis, Q is the intercept along the y-axis, R is the intercept along the z-axis, PQR. So we are defining HKL as 1 upon P, 1 upon Q and 1 upon R, given the condition that they are presented in the smallest possible integer number. How? Let us understand. Let us understand. Forget about this theory. Let's come to the point. Suppose this is a plane. Can you see this plane? This is x-axis, this is y-axis, this is z-axis, and this is a plane. This is A point on the x-axis, B point on the y-axis, Z point, C point on the z-axis. Suppose the value of OA, OB and OC is given. OA is suppose 2A upon 3. OA is suppose, yes, good evening, listen everybody. Yes, listen, gate. Suppose it is OA is 2A by 3, OB is 2B by 5 and OC is 2C by 3. So the first thing you have to do is you have to take out the factor. Okay, what is the factor? 2 by 3. Here it will be 2 by 3, the factor of intercept along x-axis. Here it is 2 by 5. Here it is 1 by 3. These are the factors. Now you reverse them, 1 upon P, 1 upon Q, 1 upon R. Reverse them. So it will become 3 by 2, 5 by 2 and 3. Hello? So what is P? 2 by 3 A upon A, you have taken the factor. What is Q? Along y-axis, 2 by 5 A upon, this should be B and this should be B. 2 by 5. This should be C and this should be C. So 1 by 3. Now you take the reciprocal. If you take the reciprocal, it become 1 upon 2 by 3 as 3 by 2, 1 upon 2 upon 5 as 5 by 2, 1 upon 3 as 3. So HKL, the Miller indices you are defining as 3 by 2, 5 by 2, 3 by 1. But this is not an integer number and you have to represent it with the smallest possible integer number. So multiply by 2. You multiply by 2, it becomes 356. So 356 is going to be your final Miller indices. Are you able to follow this? Now can you do it in the examination? Very easy, na? Can you do it? So how we are defining the spacing between a plane HKL and the other such parallel planes passing through the origin is called the interplanar spacing. Okay. It is noted by D suffix HKL and it's given as A, where A is the intercept of the unit cell. A divided by under root H square K square L square. Simple formula, put the values every alternate year they are giving the question, just put the values, you will get the answer. So this is the interplanar spacing. Very easy. Halwa type question. For tetragonal unit, there is a simple difference. Okay. So it's going to be 1 upon under root H square plus K square plus L square. In bracket, there is A square plus C square if it is a tetragonal unit cell. The member of family of planes HKL have the same interplanar spacing. So if the Miller indices are defined, interplanar spacing is going to be fixed. Okay. Are you reading this? Crystal imperfections. Crystal imperfections means till now what we have discussed is the ideal possibility. But in practical world, there cannot be any ideal possibility. Always there will be some issues, some problems. So those issues, those problems with the arrangement of atoms in the crystal, we are defining as crystal imperfections. Now these crystal imperfections can be defined as, yes, just a moment. Okay, no problem. So we can have various types of imperfections, maybe point imperfection, maybe line imperfection, maybe you can say surface imperfection, volume imperfection you can have, but we'll be focusing on only on point imperfection, that is in our syllabus, point imperfection only. Now point imperfection is defined as the zero-dimensional imperfection, point imperfection. They occur in imperfect points like regions in the crystal. And why we can have point imperfection? The reason is maybe thermal fluctuations because of temperature, quick cooling of material from the high temperature, so the rate at which cooling is done, that may be the reason. Deformation of the material by forging. So if any mechanical process or chemical process is done, definitely always there will be some imperfection. Last, displacement of atoms in a material with the bombardment of high energy particles. For example, alpha particles. I am just telling you one example. Okay. Now we talk about the vacancies. Vacancy means what? If somebody is not present, when somebody has to be present, that is called vacancy. Hello? Are you getting this or not? Suppose you don't want me here and I am not here. That is not a vacancy. But you want me here and then I am not here, then it is a vacancy. Yes, like a hole. Very good. So it is the simplest of all the points defects. It occurs when there is an empty site in the crystal structure where the atom has to be present but it is not present. It is just a missing or the vacant atomic site, something like this. There is no atom present whereas it has to be present here. Then we have interstitial defect. Now I will relate this interstitial defect with Salman Khan, so that you remember it just, okay? I am not a fan of anybody. So what happens? Have you seen any reality show? Have you seen any reality show? TV reality show you must be watching because you have lot of time apart from your studies. So whenever he is coming to any of the reality show, he is not sitting on the specified sofa. Either he is lying on the ground or he is leaning like this or doing something like that. So when atom is not present at the actual site or location and it is present elsewhere, this is called interstitial defect. It occurs when an atom occupies a definite position in the lattice which is not normally occupied in the ideal crystal structure. This is called the interstitial defect. The interstitial atom may be either a normal atom of the crystal or a foreign atom. Something like this. Every atom is sitting here in the best possible way, but Salman Khan is lying on the ground. I don't know why. I hope you are getting my point, making fun of this. But take it objectively. Substitutional defect. Substitutional means if some particular atom is replaced by another foreign atom. Are you getting this? Another foreign atom. If an atom is replaced, this is called substitution. When a foreign atom replaces or substitutes a parent atom of the lattice site in the crystal, then this is called substitutional defect. Frankel's defect. Frankel defect is going to be possible in ions, okay, where positive and negative ions are present. Then it is called when an ion displaced from a regular location to an interstitial location in the crystal lattice, known as Frankel defect. So ion, you understand, it is going to be both positive and negative ion. Now ion crystals have two different kinds of ions, which are cations and anions. Cations are smaller, I told you already, while anions are larger in size. Then we have Schottky defect. This defect occurs when a pair of cation and anion is missing from the ionic crystal. Now this is very interesting. Okay. So if somebody runs away to do the court marriage, it is something like this. Positive and negative ion left the home, left their individual home and went away and gone for a court marriage. So it is something like this, Schottky defect. The electrical neutrality of the ionic crystal is maintained by the vacancy of the missing pair of ions. Schottky defect occurs in alkali halides. Important points, something like this. Let us compare the Frankel's defect and Schottky defect. It occurs in ionic solid. It also occurs in ionic solid. Let me change the color of the pen. It is interstitial. It means the ions are not losing the material. Are you getting this? And it is a vacancy type defect. Not the material, the cell I am saying. Okay. It occurs when the cations are displaced into the interstitial positions. It occurs when a pair of cation and anion are missing from the ionic crystal. It occurs in CaF2O and silver halides. It occurs in alkali halides. I hope it is clear. So this is all from my side, friends, for the today's session. I hope you enjoyed the session. You got some confidence about this subject. I am not in a hurry. I am not running after anything. I am not shouting and I am not demeaning anyone. I am just trying to help you out so that you get some confidence if you have not got that much confidence in your preparation. So we'll be coming up with the second part of the discussion for this material science for engineering services prelims examination. Stay connected. But before we leave for today, some important information about the BYJU'S Exam Prep Rank Predictor tool for the GATE 2023. 15th of February 2023, it is going to be active when the official... Okay. Is there any problem with this? Is there any problem? See, if you have an alternate GATE, I'm just telling you very frankly, I'm not having any ego that kind of, because you may have better resources also, you may have better books also, but if you think you have any alternate, you can follow that. And if you get after attending this session, you just try the previous year questions, you will understand whether it is enough or not. Are you getting this? 6-7 days remaining, how much you can do the effort? Okay. Anyways, so get yourself registered, go to the BYJU'S Exam Prep site. There is a pop-up notification, follow that and say notify me. You will get the notification when it is live. So everybody just hit the like button before you leave, hit the bell icon so that you do not miss any of the important session, and subscribe to BYJU'S Exam Prep if you have not subscribed. The PDF of this session will be available. Thank you, Sachin. Thank you. Thank you. What I'm saying is, yeah, Telegram channel, you can join for the PDF. That is Electrical by Ashutosh Sir. That is my name. You will see my photograph on the channel. Okay, profile picture, and you can join it. How to join my Telegram channel? Just go to the Telegram app. In the search option, write my channel name, Electrical by Ashutosh Sir, and you will see my photograph. You can join it. Next session, we are back to back. We are having the sessions for non-tech also, technical also. We are having back-to-back sessions. Stay connected. Stay connected to BYJU'S Exam Prep. Every time, how you have to keep update yourself. Just subscribe to the channel. Go to the session. Go to the channel and see what are the upcoming sessions. You will understand. So next week is completely going to be full packed with the action. Sachin is asking for tech when it will happen. Tech, it will be after 13-14 also. After Tuesday only. After Tuesday only we can plan. because already we are having current affairs and material science on 13, that is tomorrow. Okay, so if Tuesday possible, then Tuesday, otherwise maybe Wednesday, but very soon we are going to do it. Okay, so thank you so much once again, take care. But before we leave, if you want, then you can subscribe by scanning this barcode also. Thank you so much. Thank you. Yeah, we can plan in night time also, no problem. Just give me some time. Let me discuss with the team. Madhua. Sorry, what is your name? Madhura. Okay, sorry. Madhura. Perfect. Thank you. Thank you, everybody. Take care. Thank you. See you again.